Welcome back, geology fans. If you live in an earthquake-prone area, you may not know it by looking around. If you live in a volcanically active area, however, you will probably notice a possibility of volcanoes, lava flows, ash deposits, fumaroles, hot springs, boiling mud, and the other features associated with volcanic activity in your area. So, though volcanoes may be sublimely frightening to us, at least the places of risk are more physically obvious than the earthquake-prone areas. Not only that, but volcanoes, though not perfectly predictable, are much more predictable than the less sublime earthquakes. But what about a volcano do we need to be worried about? And should we only be worried when an eruption is actively occurring? Obviously, the force of an explosive eruption is enough to kill within a certain range, as David Johnston found out on the morning of May 18, 1980, when Mount St. Helens erupted with a lateral blast that took out his observation post, killing him and over 50 others. Obviously, getting caught in a lava flow can kill as well. Though a Hawaiian-type eruption is not as dangerous as the more explosive eruptions. One could still be burned by lava, especially if you fall through a skylight of thin rock into a flowing lava tube below, or have a town burned down if it's in the way of a lava flow. But these two most obvious lethal aspects of blast impacts and the heat of lava are far from being the most deadly manifestations. Many people have been killed by volcanoes not erupting. The best analogy for magma coming up to produce a volcano is a can of soda that has been shaken up to disturb the CO2 in solution so that if you open the top and release the pressure, you get an eruption. The soda in the can is like molten rock underground, which we call magma, and the erupted soda is like molten rock on the surface, which we call lava. Magma has dissolved gas, and just like soda, there is a lot of CO2 dissolved in magma. But in a magma, water is dissolved and released as a gas as well. Though water and CO2 are the two most common dissolved gases in magma, it is the hydrogen sulfide gases which give volcanic areas a rotten egg smell sometimes. The thing is, I could take my shaken up soda and slowly release the seal at the top, and there will be a long hiss of escaping gas before the magma soda makes it up to erupt lava soda all over the place. That escaping gas part has killed thousands of people without an actual eruption taking place. Our first case study is Mammoth Lakes, California, where a park ranger getting into a snowbound cabin nearly passed out from CO2 suffocation, which led the USGS to begin monitoring CO2 gas output in the area. A few years later, a park ranger fell down a fissure filled with CO2 gas and died. And one of the two rescuers also succumbed to the fumes, while the other rescuer was barely brought back from the edge of death. So two have died at this location because of CO2 gases. Whole areas of forest have died from having their roots choked with CO2 gas. This is simply from too much CO2 settling into fissures and low spots and suffocating all within the area. Even more CO2 can be stored and then released with the help of water. Lake Nyos in 1986 was a lake formed in a volcanic caldera, a hole often formed at the center of a volcano when the magma chamber below gets evacuated in an eruption, and the surface collapses into the empty space left behind. I'll briefly pause to note this is another possible volcanic risk, the collapse of the caldera edge, though this is a rare and unlikely event to experience. But within the caldera of Lake Nyos, a lake formed, which still has an active magma chamber below it. The magma chamber acts like that soda, which is being slowly opened and releasing CO2 to the bottom of the lake, where the colder temperature and higher pressure allows the CO2 to dissolve efficiently. In 1986, enough CO2 had dissolved into the deep lake waters that when a landslide came off the edge of this lake, it stirred up the lake like shaking a soda and causing the gases to come out of solution. Because CO2 is more dense than average air, this cloud of carbon dioxide slid down the side of the volcanic mountain, down into the valley that led right into a nearby town. People coming to the town in the following days were shocked and bewildered to find almost 2,000 people and over 7,000 cattle dead, along with many other dead animals. But there was no sign of an eruption, nor of disease, nor violence. The survivors only reported a breeze, and then difficulty breathing or even losing consciousness. This was all due to the volcanic lake belching out enough gas to suffocate the lower parts of the town, and it doesn't take too much CO2 to cause you trouble. At 2 to 3% concentration of air, CO2 starts to be noticed by a shortness of breath with any exercise. Passing 3%, breathing becomes more difficult, even at rest, and your breathing begins to deepen and accelerate. Reaching 5%, breathing is very difficult, and headaches begin, followed by sweating and increased heartbeat. Getting up to 7.5%, all of the above is accompanied by dizziness, weakness, mental deterioration, ringing of the ears, and a desire to fall asleep. Following this, as you get over 8%, vomiting, loss of consciousness, convulsions, and death, which is pretty much guaranteed with just a few breaths at maintained levels of 25%. And volcanoes can cause local atmosphere to exceed 25% CO2, and in such areas one must avoid lower valleys, basins, caverns, and holes, which is extremely important for pets like dogs, who are closer to the ground, and children for the same reason, and they're more susceptible physiology. So suffocating gases without an actual volcanic eruption can be one of the most dangerous aspects of living near volcanoes. If you see a fumarole, a hole with gases that smell like rotten eggs coming out of it, often with a rim of yellow sulfur that deposits out of the vapor onto the edges of the hole to make the iconic sulfurous brimstone, if you see that, don't stick your head in and expect to breathe. The gases can help alter volcanic rock into rusty hematite, white gypsum, along with yellow sulfur to make some wonderfully colored landscapes, though. But that sulfur also comes out with an actual eruptive event, and that leads to another less obvious risk of volcanoes. Volcanic ash can be ejected with such force and heat to drive it up above the part of our atmosphere involved in weather, and can stay up in the atmosphere for years, spreading around the world. The sulfur compounds can turn to sulfate aerosols that are small particles that act like tiny mirrors, reflecting light back to space, thus cooling the planet. When Mount Pinatubo erupted in 1991, a resultant drop in global average temperature took place over the next 2 years. Pinatubo was a pretty large eruption that blasted straight up and was located near the equator, all of which help inject planet-cooling ash into the upper stratosphere layer of the atmosphere, and then spread around the world. The 2 years after Pinatubo, the planet experienced a cooling period of almost half a degree Celsius. One of the ways climatologists get a handle on how sensitive our planet's climate is to perturbations is by observing how volcanoes force the system and how it responds. Then again, Tambora was a similar but larger eruption in 1815, causing 1816 to be called the year with no summer, with resultant starvation in parts of the world. We can link deaths to such volcanically induced climate change, and so consider volcanoes' climate-changing ability a risk. It must have been even worse around 70,000 years ago when an even larger eruption took place near the equator at Toba Lake of Indonesia. This may have decimated the global human population of the time and caused a real risk to our modern survival. Man truly lives by geologic consent, and life itself on this planet lives by the same geologic consent. It was about 251 million years ago that 70% of all species on land went extinct and 97% of all marine species died out. Though many explanations have been put forth, the leading hypothesis is that this nearly complete extinction was caused by an enormous volcanic eruptive cycle in Kamchatka, east of Siberia. The amount of ejecta, the material put out of the volcano, dwarfs even the largest, more recent eruptions. Such giant outpourings of lava are called volcanic traps, and a recent paper has identified about 10 such traps through all of geologic history. The Kamchatkan trap, 251 million years ago, though, seems to have hit large beds of coal, which flash burned and spewed toxic fly ash all around the world. So volcanoes can also vaporize and burn areas, adding even more ash and gas and toxic material to the air, which clearly can be environmentally devastating. A volcano can turn an inert toxic substance mobile and kill on a global scale. But the most deadly modern eruption shows us that volcanoes can also kill through poisoning you from the ejected material itself. It's hard to believe that such a beautiful rift could be such a valley of death. But this is the source of the basaltic volcano Laki, which erupted in Iceland in 1783, belching out hydrofluoric and sulfuric acids over 8 months and poisoning the land to such an extent that over half of all Icelandic livestock perished as their food withered away. And then the people began to starve. By the end of the 8-month eruption, it had ejected enough material to rank as a 6 on the Volcanic Explosivity Index, or VEI. Let's quickly note this index, which goes from 0 to 8 and is based on the amount of material ejected out of the volcano, the ejecta, over what time and to what height. Here we see a volume comparison and see that Laki, being around VEI of 6, was a substantial eruption in 1783. Starting on June 8th, it began to affect England by June 23rd, giving a fog to the air that reportedly made the sun look like a clouded moon and cast a rust-red glow all around, becoming brilliantly red at sunrise and sunset. This fog persisted from June 23rd to July 20th in England. Ben Franklin wrote of this persistent darkening mist over Europe and much of North America that would not dissipate with the rising of the sun like normal fog and cast light so weak he could barely brown a piece of paper with the sunlight focused through a magnifying glass. He later gave a talk about how the ground in summer was so chilled by this diminished sunlight that the 1783-84 winter became the earliest onset, longest to last, and most brutally cold in the American records. With poor harvests around the world, starvation was not limited to Iceland, though it was, of course, worst there, where not only half of all livestock died, but almost a quarter, 1 in 4 people, died in Iceland. Adding up the other deaths that can be linked to this eruption, it probably ended up killing tens of thousands more people in Europe, and probably affecting the monsoons enough to cause droughts in India and also around North Africa. Iceland is like the seafloor, a mid-ocean ridge seafloor, exposed above sea level. The potential for Iceland to give us another fluoride and sulfur-rich Laki-like eruption is actually fairly good. When you notice a Icelandic eruption starting up, you might pay a little more attention to it. Now, the gases and ash can travel the farthest from the eruption source, but larger material is found closer in. We call the smallest ejecta ash. Then we go to lapilli, cinders, and the largest are bombs. These bombs get ejected with supersonic velocity and travel ballistically for kilometers before smashing into the ground. Clearly, you don't want to be hit by any rock hot enough to be glowing, but even a fairly cool bomb can kill from kilometers away from the source, as it acts like a ballistic kinetic weapon. The city of Pompeii, killed by the 79 AD eruption of Mount Vesuvius, was hit by such bombs and hot cinders before being buried in ash, which combined with the CO2 and other gases helped suffocate the people of that town. On the other side of Vesuvius, the town of Herculaneum was destroyed by yet another way that volcanoes can reach out to kill you. Herculaneum was taken out by a pyroclastic flow. Now, this is the most deadly manifestation of a volcano in the immediate vicinity of an eruption. Much of the material ejected is too heavy to remain suspended in the air and falls to the ground to mix with landslide material to come racing down the side of the volcano. These often exceed speeds of 150 kilometers an hour, and if you aren't killed by the impact, the hellish temperatures and suffocating ash and gas will do the trick. In 1902, the town of Saint-Pierre was completely destroyed, like Herculaneum was in 79 AD, by such a pyroclastic flow. In fact, that flow was so hot that it actually glowed as it came down through the town. In such a case, we can give it a special name of a nuée ardente, French for a glowing cloud, a very hot pyroclastic flow. This fire-broken flow killed every person in the town of Saint-Pierre. Well, Everyone but that murderer who was in a bomb shelter as a solitary confinement punishment that in the end saved his life, and he was released and became the famous man who survived Mount Pelée and toured with the circus. The Crofts, a husband and wife volcanologist team who undoubtedly have seen more erupting volcanoes than any other humans before them, were killed by a pyroclastic flow from Mount Unzen in Japan in 1991. Volcanoes, often having relatively steep and often weaker slopes, will also produce simple landslides from seismic tremors set off by the erupting volcano, though Mount St. Helens showed us just how big of a landslide can be produced. That one took the whole side of the mountain off and let the magma escape violently in a lateral blast. And so we've seen that volcanoes can kill through direct explosive impact, the heat of lava, suffocating gases, climate change forcing, vaporization of toxic materials, ejection of toxic materials, acid rain, massive ashfall, volcanic bombs, pyroclastic flows, and that brings us to our last volcanic risk. As we can see from various images of volcanoes, many of these have snow and even glacial ice at their summits. When a volcano erupts, the heat emitted melts this ice, which can run down the mountain slope to become a mud flow mix of water, ash, mud, rocks, trees, houses, and anything else picked up on its rush down the mountain. Their simple volcanic origin means these mud flow and debris flows are often heated, hot mud flows. We give these the special name of lahars. The historically deadliest lahar occurred in Colombia in 1985 when the volcano known as Nevado del Ruiz melted the ice at its summit, sending hot mud flows down the river valleys, one of which ran all the way to the town of Armero, almost a kilometer away, and buried large sections of the town, injuring 5,000 people, but killing around 23,000. The section of Armero that was not hit was the high ground, which gives us the depressing thought that if the people of Armero had better warning system and evacuation plan in place, 23,000 mothers, fathers, brothers, sisters, and cousins would have been saved. And this is a problem for geologists when they have located an area of risk. We don't want to unnecessarily alarm people if the risk is not that great, but we don't want to underplay the risks either and have to walk a tightrope. With a risk like earthquakes, where the timing of the event is uncertain, we might want to focus on mitigation over prediction. But with volcanoes, we have had much better ability predicting in recent years, and thus we can rely more on planning around shorter-term predictions. When we come back next time, we will investigate what we look for to predict a volcanic eruption, here on Earth Explorations.